So resistance. Okay, so resistor, charge flows through a circuit. Objects like light bulbs draw some of the energy or power. These objects are called loads on the circuit. So resistor is a load. It takes some of the energy. It slows the current flow or resists the current flow. Now, charge is able to move more easily through some materials than others. So that's the resistance of the wire itself. So characteristics that affect resistance, there are 4 of them. This is the first 2. All right, so length, if the length of the wire increases, resistance increases. We're going to do a little demo. We're going to get up and moving around if we have time, and we'll go through some of these factors and see how that would affect it. But if you think current flow is electrons flowing throughout the circuit. So as they flow through the wire, they're bumping up. What are wires made up of? Metal. What's metal made up of?
Iron.
Some metals made of iron. I'm thinking smaller. Think back to chemistry.
Atoms.
Atoms. Good job. So wires are made up of atoms. So as the electrons move through the wire, they're moving in between. They're trying to move through the atoms. Now, if you've got some materials that have atoms configured in a certain way, electrons are going to bump. They're not going to be able to flow nice and freely through that wire. They're going to bump more. That's going to increase the resistance. If you have a longer piece of wire, you're going to get more bumps. So it's going to take longer. There's going to be more bumps for it to go through. That's going to increase resistance. Same with cross-sectional area. That's the diameter. So if you've got a really thin wire versus a really thick wire, if you have more room to go, the electrons are going to bump less. If you think a good analogy is the hallways. When we're all leaving Alumni Hall. Well, we all leave Alumni Hall, there's 2 great big doors there. Or 4 doors, isn't there? But there's lots of room for us all to get out. And then what happens is we get into that little hallway by the cafeteria and we all bottleneck. And there's no way for us to get through. If we had a wider hallway, we could get through much easier, couldn't we? So that's cross-sectional area. If we tried to line everyone up in the school and have them go through this classroom on their way out of Alumni Hall, well, that would make it even more restrictive, because you can only go through these doors here one at a time. So that would slow things down even more. So that would restrict the flow of students. So if we increase resistance, we restrict current flow. Other characteristics, temperature and material. All right, so temperature, as temperature increases, what happens to things as they get hotter?
They go faster.
They go faster, but I'm thinking a wire or water or anything. When it gets hotter, it expands. The distance between the particles expands, you have less bumping. Material, different materials are going to have different structures that are going to allow electrons to either flow more easily or less easily through them. Which brings us to this, our last equation. All right, so resistance is equal to potential difference over current. This is the same V and I, potential difference and current, that's in the other formulas. So again, we can combine the 3 formulas. If I give you some bits of information that use one of the other formulas, you can solve and then substitute into this formula, which is something that they like to do. Now, for resistance, it's measured in ohms. That's what that symbol there stands for, ohm. So I'll take a moment and say it because it's funny. Ohm. All right, that's enough. So here's an example using that formula. That's on the tape, I hope you know. So we use the formula. So we have 9 volts over 0.006 amps, which gives us 15. Oh, that's not supposed to be like that. 1,500 volts per amp, or 1,500 ohms. That's equals. I don't know why I converted it. Okay, which leaves us An assignment. I'd like you to read those pages and answer those questions. I will go back.